Welcome. Thank you very much for joining us for today's webinar, Japan and Australia Opportunities in Hydrogen and Low Carbon Steel. My name is Masu Sugiyama. I'm an associate professor at the Institute for Future Initiatives at the University of Tokyo. I'll be moderating today's webinar. Today, we explore the role of hydrogen and low carbon steel in decarbonization. The world makes efforts to cut carbon dioxide and other greenhouse gas emissions have to address so-called hard-to-abate sectors. Low carbon steelmaking and hydrogen are going to play a crucial role. It is our great honor to have the leading academic experts as well as the industry experts, both from Japan and Australia, the two key countries in this technology area. Before going into the actual content, I'd like to make a few housekeeping announcements. This is a Zoom webinar, and you can ask questions by typing into the Q&A box. Probably you have already seen this in the title slide. We have a great lineup of speakers today, but unfortunately, we may not have enough time for many questions. So you are welcome to type in your questions into the Q&A, and our speakers might answer some of your questions by typing. But if this happens, please understand that your identity or Zoom name could be disclosed to all other participants. Also, please, because of the time limitation, your questions may not be answered. Almost 900 participants registered for today's event. This is a testament to the interest in hydrogen and the decarbonization in Japan and Australia. Today's webinar is jointly hosted by the University of Tokyo Graduate School of Public Policy and Institute for Future Initiatives. And from the Australia side, Australian National University, Crawford School of Public Policy, Institute for Climate, Energy, and Disaster Solutions. First, I'd like to invite Vice-Chancellor Brian Schmidt to give his opening remarks. Professor Schmidt is Vice-Chancellor and President of Australian National University. Professor Schmidt is one of Australia's most eminent scientists. He received the 2011 Nobel Prize in Physics, alongside many other academic awards and distinctions. Professor Schmidt spent most of his academic career as an astrophysicist at the ANU Mount Stromlo Observatory and Research School of Astronomy and Astrophysics before becoming Vice-Chancellor. So it is our great pleasure to invite Professor Schmidt. Please.
All right, thank you, Associate Professor Sugiyama. Welcome, everyone. I am very pleased that the University of Tokyo and the Australian National University are able to host this seminar today, albeit virtually, but it would be very difficult to have so many people together, I think, if we did it the old way. I am looking forward to being able to welcome, though, colleagues from the University of Tokyo to our campus in the near future, now that our international borders have begun to open. Before I begin, I'd like to acknowledge and celebrate the first Australians on whose traditional lands and airwaves we are meeting today, and that's the Ngunnawal Ngambri people, and I pay my respects to elders past and present. The Ngunnawal Ngambri people have been here on our campus for over 20,000 years, and they lived and saw climate change in ways that I think the rest of us really struggle to imagine, but are going to find out in, I'm afraid, the decades to come rather than the millennia that they saw. Australia and Japan enjoy an especially close relationship that has been forged over many decades, and indeed I have benefited personally from that. Australia's core economic and strategic interests lie in the Asia-Pacific region, and the ongoing relationship between Australia and Japan is absolutely central to these interests. Beyond the close relationship that our countries and governments share, strong connections between our universities, our industries, and communities play a vital role in ensuring our countries keep and build on our already close ties. The relationship between Australia and Japan has been continued to be built on by the Australian National University for more than a half century. The ANU's Japan Institute is Australia's largest network of distinguished and emerging scholars with expertise in the region. Research and teaching spans a number of disciplines, including art, economics, environment, health, history, law, languages, and politics. Of course, there's huge amounts that we do in science together as well. We have the Australian Japan Research Center, housed within the ANU Crawford School of Public Policy, which is the center of research, teaching, and outreach on the Japanese economy in Australia. The center's mission is to better understand the Australian-Japan relationship and the place we both have in the Asia-Pacific economy. It was established in 1980 with support from the governments and business communities in both Australia and Japan, and our research encompasses trade, finance, macroeconomics, as well as international economic relations. Most recently, the center launched a major report on reimagining the Japan relationship, an agenda for Australia's benchmark partnership in Asia, and that was commissioned by the Australian-Japan Foundation. This report highlights approaches for Australia to think about the Japanese and what is needed to build the institutional support and infrastructure that is necessary to continue to foster our bilateral relationship and indeed grow it to meet the needs of the coming decades and even century. A focus of our work with Japan is also through our strategic partnership with the University of Tokyo. The University of Tokyo is one of our most important strategic partners, and we look forward to strengthening this relationship even further. I certainly look forward to being able to come to the Hongo campus one more time, since it's been a few years since I've been able to be there in Tokyo. A key shared challenge facing our two countries is that of climate change. Australia and Japan have been longstanding partners in trade and investment in energy-related products and in energy-intensive goods like steel, which is the focus of today's event. It is inevitable that as both our countries transition towards net zero emissions, the nature of the trade and investment between our two countries will change. And here at ANU, we're redoubling our efforts to provide the ideas and advice that will help contribute to this transition to be a successful one. Through the efforts such as the Institute for Climate and Energy and Disaster Solutions, led by Mark Howden, who can I say has been a very busy vice chair of the IPCC report this week, we are advancing innovative solutions to address climate change, energy system transition, and disasters. And we're doing that through approaches to research, teaching, and policy engagement that cross traditional disciplines. Australia and Japan also have much to learn from one another in responding to climate change. The ANU and the University of Tokyo are at the forefront of research and engagement in mapping how to respond to climate change within our two respective countries, as well as what the transition to low carbon economies means for the relationship between our two countries. It is an honor for me to open our event today, Japan and Australia, opportunities in hydrogen and low carbon steel. And I would certainly like to extend my gratitude and thanks to our colleagues at the Institute for Future Initiatives and the Graduate School of Public Policy at the University of Tokyo, who are co-sponsors of this event. I'm looking forward to continuing our collaborations together, and I'd like to thank all our colleagues at the Institute of Climate, Energy, and Disaster Solutions and the Crawford School of Public Policy at ANU, who have helped organize today's seminar. We have some excellent speakers from both our institutions, coupled with contributions from industry partners. I would also like to welcome Mr. Hiroyuki Tezuka from the JFE Steel Corporation and the Japan Iron Steel Federation, and Mr. Christopher McMahen from Fortescue Medicals Group. Today's speakers are going to share with you Japanese and Australian perspectives on hydrogen and low carbon steel, as well as speaking about the opportunities for industry and research collaboration. Here at ANU, as the nation's national university, we're ready to contribute to this work really any way that we can and any way that people think's useful. And I look forward to seeing how your efforts develop to work between our two countries and indeed our two institutions. And I'm sorry that I'm not going to be able to stay for the entire duration of the seminar, but I have no doubt that these panels discussions today will be of incredible value as we work towards this shared goal, a shared goal that isn't just this year, but it's going to be for the decades ahead. And so without further ado, I'd like to hand back the mic to Associate Professor Masa Sugiyama. Thank you, everyone, and look forward to hearing of the results.
Thank you, Vice-Chancellor Schmidt. Thank you very much for your warm welcome remarks. I've been to ANU Canberra campus. It's a wonderful place. I wish I could visit there in the near future again. And yeah, let's move on to the first session, which is titled Hydrogen and Low Carbon Steel, Japan and Australia Perspectives. In the first session, we have two speakers, Associate Professor Ryoichi Komiyama from the University of Tokyo and Dr. Emma Aisbett from ANU. Our first speaker is Professor Ryoichi Komiyama. He is an associate professor at the Department of Nuclear Engineering and Management at the University of Tokyo. He obtained a PhD degree of electrical engineering from the University of Tokyo in 2003. He is a researcher on energy modeling and energy and electric power system analysis. So Professor Komiyama, please, the floor is yours now.
Thank you, Mr. Chairman. Firstly, I am delighted to have a distinguished opportunity to make a presentation today and would like to greatly thank the people organizing this great event. First, let me emphasize the principle for decarbonization. In principle, according to Kaya's identity, carbon neutrality requires energy conservation, fuel switching, and CCUS. And these three components are important to be implemented in energy system. On the other hand, in reality, achievement of carbon neutrality needs to be discussed simultaneously considering economic efficiency and energy security. In this context, hydrogen is expected to be a socially selected in an energy system for the future as a promising option. This slide shows the current status of greenhouse gas emission and its reduction policy in Japan. Japan currently pledged 46% greenhouse gas emission reduction by 2030 from the level of 2013 and net zero emission by 2050. And essentially the challenge of climate change could be solved by energy system transformation. Currently in Japan, industrial sector accounts for majority of the emission, and particularly steel making sector is the largest source of emission in industry, dependent on coal, namely coking coal. Therefore, accelerated adoption of clean energy technology across entire energy sector, including industrial sector, is significant for carbon neutrality. According to the governmental energy policy for achieving carbon neutrality in Japan towards 2050, the basic strategy in Japan consists of electrification, clean fuels, and CCUS. As far as the sectors having a difficulty in electrification, innovative options such as hydrogen, synthetic fuel, and CCUS are planned to be introduced. In addition, Japanese government announced action plans for 14 priority fields specified as indispensable for Japan's carbon neutrality goal by 2050. In the field, hydrogen is highlighted in power generation, steel making, mobility such as vehicle, maritime, aviation, and hydrogen production through both electrolyzer and nuclear. I would like to have some comments on hydrogen. The bottom line is that hydrogen has multiple advantages in terms of environmental compatibility, clean carbon reduction in hard to abate sectors such as steelmaking sector, and resilience. That is diversification of supply chain and productivity that is producible from various sources, and processability. Hydrogen can become ingredient for various synthetic fuel. However, it should be noted that in the physical aspect, hydrogen has a difficulty in transportation due to low energy gaseous forms and stressful material, namely embrittlement. Therefore, viable mass transportation infrastructure is required for affordability and accessibility. The challenge of hydrogen in Japan consists of research and development, infrastructure development, and cost reduction. For hydrogen per se, the establishment of supply chain infrastructure is critical for full-fledged penetration of hydrogen, such as water electrolysis, hydrogen liquefier, hydrogen transport carriers, fuel cell, hydrogen ammonia gas turbine. And depending on the requirement of the user of hydrogen, the type of hydrogen production will be selected in terms of carbon intensity and cost. Currently, green hydrogen, that is utilizing renewable electricity, could be most acceptable in environment, while blue hydrogen produced with CCUS could be currently more economic. Generally speaking, green hydrogen, namely renewable-based hydrogen, is socially most acceptable type of hydrogen. Currently in Japan, largest class hydrogen production in the world, Fukushima Hydrogen Energy Research Field was completed at Namie Town in Fukushima Prefecture, Japan, producing as much as 1,200 cubic meters of hydrogen per hour using renewable energy. Though green hydrogen is a socially favorable option, we need to resolve the challenge for green hydrogen, that is cost reduction in renewable and hydrogen infrastructure. As far as in Japan, generally, renewable energy cost is generally expensive, and import of green hydrogen from foreign country could be a possible option. In addition to green hydrogen, yellow hydrogen, that is a nuclear-based hydrogen, is a possible option as well in Japan. Through the application of multiple technologies such as high temperature electrolysis, thermochemical water splitting, advantage of nuclear-based clean hydrogen supply can reduce supply uncertainty and the impact of fuel price spike, which the world has been currently facing. For example, high temperature gas-cooled reactor, HTGR, one of the types of small module reactor, SMR. This is a higher safety reactor based on passive safety design, that there are no radioactivity release beyond the regulatory limits. And HTGR has a characteristics that the outlet coolant temperature reaches 950 centigrade, and 80% of reactor thermal power can be utilized for hydrogen production, power generation, and desalination. Like this, nuclear-based hydrogen could greatly contribute to enhance self-sufficiency of hydrogen supply and decarbonization in Japan. Moving on to the hydrogen demand side, one of the expected role of hydrogen is utilization in mobility. Hydrogen in mobility is highlighted in long-distance transportation technologies such as buses, trucks, aviation, and ships. And key requirements for fuel cell vehicle, which Japanese industry has a competitiveness, include compact cells, high reliability, and affordable cost. However, electric vehicle, EV, competitive technology to hydrogen will impact the pathway of hydrogen penetration in transport sector for the future through the improvement of energy densities of batteries, through the development of all solid-state batteries and fluoride-ion batteries. Among carbon emission hard-to-abate sector, extensive carbon reduction in steel-making sector determines the success of the achievement of carbon neutrality. In steel-making sector, massive carbon reduction is not achievable without innovative steel-making process. Innovative steel-making technology is still at the stage of demonstration or prototype, like facilities utilizing CCUS and hydrogen, such as blast furnace utilizing hydrogen and CCUS, hydrogen-based direct reduction ion, DRI. It is important to continue the technical effort to commercialize those technologies. And hydrogen in power sector is expected to play an important role in Japan as well. Essentially because in Japan, extensive penetration of renewable energy is economically and socially not easy to decarbonize electricity. Therefore, clean imported hydrogen from foreign countries is a promising option to decarbonize electricity through co-firing of hydrogen or fuel ammonia in thermal unit and monofuel combustion of hydrogen and ammonia. Co-firing technology enables power system to utilize existing facility and reduce the cost, playing a role in the transition to carbon neutrality by 2050. In Asian countries, heavily depending on coal-fired power generation, coal-firing technology is expected to play an important role as well to reduce carbon emission in these kind of Asian regions. Lastly, our team in the University of Tokyo conducts feasibility study of hydrogen in optimal energy mix for carbon neutrality by using a dynamic energy system optimization model, including more than 300 technologies and energy carriers, 8,760 time slices per year in power sector. From the simulated results, basic trends are promoting energy efficiency, clean energy supply, and CCUS. However, carbon price in 2050 escalates to as much as $800 per ton of carbon dioxide. Therefore, it is not easy to achieve carbon neutrality in terms of economic viewpoint. This is a result of hydrogen demand and supply outlook in Japan to 2050 and a carbon neutrality constraint to 2050. Though the result is one of a possible scenario and is subject to change depending on the assumption. Derived from the result, hydrogen demand is boosted through the requirement of decarbonization in hard-to-abate sector like steel making sector and synthetic fuel production and industrial process and fuel cell vehicle power generation, while hydrogen supply is satisfied from import and domestic production through electrolysis. This is a possible future outlook of international hydrogen trade. In the world, energy resource availability is different depending on the country or region. Japan is basically an energy consuming country, so resource endowment is relatively limited compared with energy producing country like Australia or United States. For energy consuming countries such as Japan, import of hydrogen could be more economically affordable rather than domestic hydrogen production due to cost competitiveness and resource availability of renewable and CCUS. Based on those background, our team of the University of Tokyo estimates the potential of international hydrogen trade by using global energy model, DNA 21. According to the analysis, international hydrogen trade will grow if the cost of hydrogen transportation infrastructure declines. The results suggest that Japan potentially import a lot of liquefied hydrogen from Australia due to the geographical proximity and resource availability of the country. Wrap up. Australia and Japan have been historically establishing a good partnership in energy and resource trade, such as LNG, liquefied natural gas, steam coal, and coking coal, as well as iron ore. Australia and Japan are recommended to enhance existing energy partnership to achieve carbon neutrality together through collaborative innovative energy development, such as hydrogen, clean fuel, CCUS, and renewable. This is the end. Thank you for your kind attention.
Thank you very much, Professor Komiyama, for your excellent talk on hydrogen and also import of hydrogen from places like Australia. You have already questions lined up in the Q&A box, so please have a look. And meanwhile, let's move on to our next speaker, who is Dr. Emma Aisbett. Dr. Aisbett is a fellow at the School of Regulation and Global Governance. She is also Associate Director, Research for NEU Grand Challenge zero carbon energy for the Asia Pacific. I'm sure we'll hear about this new initiative at the ANU. As a researcher, she contributes the Zero Carbon Energy Grand Challenge focused on trade and investment aspects of the energy transition and their interaction with green industrial policy. She holds a PhD in economics from the University of California. So Dr. Aisbett, please, the floor is yours.
Thank you very much for the kind introduction. It's a pleasure to be at this exciting event today. Thank you all for your attention. I will indeed be presenting work which has arisen from the Zero Carbon Energy for the Asia Pacific Grand Challenge, of which I have the pleasure of being the Associate Director Research today. So I'd like to acknowledge at the outset that the slides and that the work I'm presenting here are the result of a wonderful team of interdisciplinary researchers, which has been a pleasure to work with. So I think our presentations will be really complementary. So we've heard a lot about hydrogen, and I'm going to focus more on the steel side of today's event. And in particular, our work looked at what role does Australia currently play and what role could it play in a zero carbon steel making future. So I'll very briefly talk about why steel matters and give a short overview of iron and steel technologies, but then really get on to focus on why we need zero carbon steel, and as I said, Australia's current and potential future role, including what are the necessary conditions to support Australia transitioning towards helping transition the steel industry to a zero carbon future. So why does steel matter? We know steel is a very structurally important material for societies. It's highly correlated with development status. And indeed, looking forward, even for countries like Japan and Australia that are already highly developed, we know there will be a large demand for steel as we build renewable energy infrastructure at an enormous pace if we are to meet our emissions reductions commitments. We also know that business as usual steel production is not an option if we are to meet our climate commitments, and indeed if we are to avoid catastrophic climate change. Steel sector current globally contributes about 7 to 9% of total global fossil and industrial emissions. In other words, if we are going to tackle climate change, we need to tackle emissions from the steel sector. To give you an idea, it's almost 2 tons of carbon dioxide equivalent emitted for each ton of steel that is currently produced using conventional technologies. So just briefly, what are those conventional technologies? I understand I'm talking to a very well-informed audience today. So just very briefly to make sure we're using the same language. The dominant technology globally is also the most polluting technology. That is the combination of blast furnace and basic oxygen furnace. The second most popular technology is direct reduction, which is usually done with a syngas, a combination of hydrogen and carbon monoxide currently. Direct reduction is up to, assuming that you keep the carbon dioxide in that syngas, up to 40% less emitting than the blast furnace stage of the sort of dominant route currently. Of course, the least emitting, or at least potentially least emitting of the current technologies that we see for steelmaking today is electric arc furnaces that are used to recycle scrap steel into new steel. And the way that this could become essentially zero emissions is if the electricity for those arc furnaces is coming from 100% renewable energy. So enormous potential there for an expanded role. Currently, scrap recycling accounts for about 27% of global steel making, with the rest coming from virgin steel. This share will increase over time as the stock of steel that's been produced increases. However, it's important to note that there are sort of technical limitations that arise from the accumulation of different metals other than iron in scrap over time if you recycle it too much. So we'll be looking later. We don't assume that scrap recycling alone will be able to get us to a zero emissions future. So some of the work that we did in the paper that I'm presenting today was to just look using the numbers, the current global numbers, what is the share of production, energy consumption, and emissions? And as you can see, the blast furnace and basic oxygen furnace combination there is the dominant share of production, but becomes an even larger share of both energy and emissions because it is the most energy and emissions intensive approach. That scrap, you can see, scrap with an electric arc furnace is already, substantially more emissions efficient, if you like, than the blast furnace route, with 24% of the actual production and only 8% of emissions. However, as we mentioned, that is not alone going to be enough to get us to a zero emissions steel industry globally. So there's a lot of research currently going on into new low and indeed zero emissions technologies. There's two that we talk about in particular, two and a half, you might say, in our paper. One is, of course, one of the main topics here today, and that is the... Yes?
Your voice is sometimes soft. Now it's working. Sorry for interruption. It's now okay, but a while ago it was very soft and I couldn't hear.
Oh, sorry, I'm not sure what's going on there. Can you hear me now?
No, really. If you speak louder, oh, that's better.
I could try yelling. Does that help?
Yeah, it works.
Okay. I'll apologize to my colleagues in the corridor later.
Okay.
So the first of the two technologies that we considered in the paper was the one that we're really interested in today, and that is the direct reduction of iron ore with green hydrogen. It's the dominant emerging technology, and indeed there are already pilot projects underway in Europe and in development in Japan, to my understanding. This has the advantage, among other things, of being similar to existing direct reduction pathways. There are, of course, differences in the chemistry when you rely only on hydrogen. For example, the reaction is endothermic, so you need to worry about how to keep the energy, keep the temperature correct. And of course, the different chemistry means that you have different ways you need to deal with the impurities from the process and remove them from the steel. Other technologies, emerging technologies worth mentioning are electrolytic pathways, both low and high temperature. Low temperature or electrowinning is similar to metal processes that are used for other metal refining other than iron. There are some processes, but none of them are generally at commercial or industrial scale for a general iron ore, non-specific. High temperature pyroelectrolysis, something that my colleague John Pye is very interested in, has theoretically lower energy requirements than electrowinning, but this is even at a lower technological development stage than the low temperature version. So, because these technologies are new and needing a lot of work and still relatively expensive, we needed to check that we really do need them immediately. And so we did some scenarios about different potential technology pathways between now and 2060. As you can see, A is the business as usual scenario, whereas scenario D is one where by 2060, we're only using zero emissions steelmaking technologies. And we wanted to know how necessary is the sort of pathway like illustrated in scenario D. And so what we did was we calculated the emissions trajectories that would be associated with those scenarios. And we compared them to what the emissions trajectories would need to be for the steel industry's share of the carbon budgets, if you like, that were available from the International Energy Agency scenarios. We looked at both the 2-degree scenario, that's the upper of those grey dashed lines, and the below 2-degree scenario, which is around 1.75 degrees warming with 50% chance. The takeaway here is that it is only the zero carbon scenario which can get us anywhere near staying within the necessary carbon budgets that the world is aiming for currently. All right, so Australia's current role, it's no surprise to anyone in this audience, Australia's current role is almost entirely as that of a raw material exporter. We are the world's largest exporter of iron ore. We produce 37% of the world's iron ore, as well as 19% of the world's metallurgical coal. In contrast, we produce only 0.3% of the world's steel. And indeed, steel production has been declining in relative and absolute terms in Australia for several decades now. So what we're interested in is whether Australia might have a different role in a zero carbon emissions steelmaking industry. And the reason that we think this is worth investigating is because Australia has phenomenal renewable energy resources. In addition to a huge landmass and low population density, we have some of the best solar radiation levels in the world, and that's often combined with pretty solid wind resources as well, which means you can get very high capacity factors for your downstream industry. Even more interesting in the case of steel, as you can see from the iron ore mines on this map, is that those incredible renewable energy resources are co-located with Australia's iron ore deposits. And why does this matter? If you look at the graph, the downward sloping curves here, you'll see that, of course, the least cost of energy production from renewable energy systems, either photovoltaic or solar thermal, is of course very closely related to the quality of that solar resource. And so this means that if you compare the solar resource in Australia with the steelmaking areas in China, for example, our renewable energy is expected to be around 30% cheaper than it is in China. So we think that Australia might have a role to play in this new industry. So the next step that we considered is really a theoretical construct, a thought experiment, if you like. And that thought experiment is, what if Australia, instead of exporting its current amount of iron ore, turned all of that into green steel using those renewable energy resources? The takeaway from this is it's a big effort, but it's not impossible. We have the land, and indeed it should be possible to get hold of the resources to do that. They're huge amounts of resources, of course, but these resources to create the renewable energy generation to support this, for example, would be needed no matter where this green steel making has happened. And indeed, there'll be less resources needed if we undertake it in a place that has very high capacity factors, like the northwest of Australia. Of course, there are many other things that go into steel making, and that is why Australia has seen a declining share of steel making over the recent decades. However, Australia has a very high skilled workforce, and new industries are much more dependent on that than they are on things like relatively low wage costs that the traditional industries have been driven by. We will need, of course, a supportive environment if we are to realize even a small fraction of the thought experiment that I've just outlined to you there. And that will require green industrial policy to address market failures. It will require what we're doing today, in particular, that is international collaboration, to make sure we solve the international market failures and to make sure that we have access to world-leading researchers and technology, as our partners in Japan are excellent examples of. We will, of course, also need supportive trade and investment policies that are both compatible with openness, but also with the needs of green industrial policy. So in conclusion, Australia does have a green steel opportunity. The extent to which we realise that opportunity will depend on the policy settings and on the excellent collaboration with our partners, such as Japan. Thank you very much. I look forward to the discussion.
Thank you, Dr. Aisbett, for your excellent presentation. So we now cover the perspective from the academia, but now today we have excellent experts from the industry, and we now move on to the second session, opportunities for industry collaboration. We have three speakers here. So our first speaker in this session is Mr. Hiroyuki Tezuka from JFE Corporation. He is Chairman, Energy Technology Committee, Japan Iron and Steel Federation. And also he's a fellow General Manager, Climate Change Policy Group, Technology Planning Department of the JFE Steel Corporation. And also he has a lot of other duties, but from March 2021, he started serving as the Vice Chair at the Environment and Energy Committee at OECD, BIAC, Business and Industry Advisory Committee. So without further ado, I'd like to invite Mr. Tezuka. Tezuka-san, the floor is yours.
Thank you very much for the kind introduction. Can you hear me?
Yes, excellent.
Okay. It's my honor to be invited this very interesting and important event between Japan and Australia. Today, on behalf of the Japan Iron and Steel Federation, let me share with you our challenges toward zero carbon steel and the issues associated with it. Next, please. Next page, please. This is the chart of the primary steel production process. Iron ore is reduced to iron by cokes, which is made from metallurgical coal by coke oven. And molten iron is decarbonized and impurity controlled by a basic oxygen furnace to make steel. Next page, please. The CO2 is an inevitable byproduct from the reduction process in the blast furnace. Carbon removes the oxygen in the iron ore, as carbon is more reactive than iron. So iron ore is reduced to iron, and carbon is combined with oxygen to form carbon dioxide. So this is a byproduct of a steel making process. Next page, please. This is very similar to the previous speaker, Dr. Aisbett, but the examples of a current steel-making process. Today, about 70% of the total crude steel is produced by primary steel route, either by blast furnace or direct reduction furnace. And the rest 30% is produced by scrap recycled secondary route by electric arc furnace. Since electric arc furnace route is use steel as input, which was already reduced. CO2 intensity of this route is 0.5 ton CO2 per ton crude steel. But primary route use iron ore as an input. So CO2 intensity is 2 tons per ton steel in the case of blast furnace, and about 1 to 1.5 ton CO2 per ton steel in DRI process. Next page, please. About 14% of Japan's total domestic CO2 emission comes from steel sector, and most of the steel-related emissions are from iron ore reduction process in the blast furnace. Switching from blast furnace route to electric arc furnace route, which emit 1/4 of CO2, seems to be a possible solution to reduce CO2 emissions. However, EAF scrap remelting route cannot be an option in Japan, since Japanese steel industry are producing high-grade, high-performance steel, which requires pure iron with very low impurity level, and it cannot be produced by scrap remelting process. More importantly, scrap availability is limited. And the secondary steel making cannot reduce global steel CO2 emission from steel industry. Let me explain why. Next page, please. This left chart shows that the steel stock in the society has been accumulated in Japan in the past half century in accordance with the GDP per capita growth. Then it was tapered out when per capita GDP reaches at 30,000 US dollars level. And the steel stock per capita reaches 10 ton per person. Japan has reached this level getting into the 21st century. Right side chart shows that this is not the case with Japan, but almost the same among all the developed countries. 10 ton steel per capita is a kind of the necessary the steel accumulation for the economic development. Today, global average steel stock per capita is about 4 tons. And China is at around that level, but India is as little as 1 ton yet. So we do need to build up more steel stock if the world follows sustainable development goals. Next page, please. We assume that the steel stock per capita will reach at 7 tons by 2050, and 10 tons in 2100. Then we can calculate the global steel stock, which is gray shaded area on this chart, using global population increase estimation. Then necessary annual crude steel production level to build such steel stock. This is shown in red line in this chart. Scrap can only be generated from the accumulated steel stock. So EAF-based crude steel production, which is shown in blue line, is sure to grow, but there is a limit in supply. Rest of the crude steel production must be filled by primary route by reducing iron ore. As you see in this chart, primary steel production, which is the green line, will be necessary around the same level as today at the level of 12 to 14 billion ton annually. This is why scrap remelting by EAF cannot be the solution for zero carbon steel. We do need the new steel making technologies which do not emit CO2 from iron ore reduction process. Next page, please. As I mentioned, current steel making process uses carbon as a reducing agent. The chemical process is shown in number 1 on this slide. The only alternative chemical process is hydrogen reduction, using hydrogen instead of carbon as a reducing agent. Then the byproduct is H2O, that is water, rather than CO2 as shown in number 2 on this chart. However, there is a big challenge in hydrogen reduction process. As shown in the slide, while carbon reduction process is a heat-generating exothermic process, hydrogen reduction of iron ore is a heat-absorbing endothermic process. This reduction, thus reduction cannot be molten. Thus the reduced iron cannot be molten and will be sticking each other during the reduction process. Next page, please. So Japanese steel industry has started multiple approaches to develop low carbon and zero carbon steel process in parallel. Let me show some examples. Next page, please. The first case is the COS50, super COS50 projects, which are the partial hydrogen reduction process, which continue using conventional blast furnace. In this process, we do not need a hydrogen supply from outside, but hydrogen is captured from coke oven gas and amplified, then inject into blast furnace. With this, about 10% CO2 emission can be saved from blast furnace. The project also aims at capturing CO2 from exhaust gas from blast furnace by using advanced CO2 capture process, which uses waste heat from steelmaking process. Combine this with CCUS, additional 20% of CO2 can be saved. In total, 30% CO2 emission reduction from blast furnace primary steel making process can be achieved. Next page, please. Course 50 was started in 2008, and a small pilot plant was built in Nippon Steel Kimitsu Works. That is left picture of this slide. There is 10% CO2 reduction was successfully demonstrated on a pilot scale. This 10% CO2 reduction is constrained by hydrogen supply from the coke oven gas. And if we can outsource more hydrogen supply, we can expect more CO2 reduction. But in that case, cooling effect by hydrogen reduction within blast furnace is to set a ceiling of how much hydrogen we can inject into blast furnace. We call this extended hydrogen reduction as a super course 50, and just started basic research to develop ultimate partial hydrogen reduction blast furnace by 2030. Next page, please. Partial hydrogen reduction process like course 50 obviously cannot achieve net zero carbon steel. It can only be possible by 100% hydrogen reduction using direct reduction furnace like this. Since the reduction process absorbs energy during the reaction, hydrogen must be preheated to more than 1,000 degrees to keep the process proceed. It is an engineering challenge to heat up a massive amount of hydrogen, which is explosive gas. Also, reduced iron is solid pellet and need to melt in the electric arc furnace for steel making process, which requires massive zero carbon electricity supply. Iron ore itself is a constraint for scale deployment since the process requires high ferrous contain high-grade iron ore, which is scarce in supply in global base. Next page, please. The third approach of our challenge is a carbon recycling blast furnace, which is JFE Steel's conceptualized and just recently started R&D process. The cooling issue of injecting hydrogen into course 50 blast furnace can be relieved by injecting carbon recycling methane rather than pure hydrogen. So this indirect hydrogen reduction in blast furnace can save as much as 30% of CO2 in our calculation. Carbon recycled methane can be produced by methanation process with CO2 captured from blast furnace off gas and hydrogen. JFE's idea is to inject hot oxygen rather than hot air into blast furnace, which is usually the case. To save energy loss within blast furnace to heat up nitrogen and the CO2 separation cost from the blast furnace of gas. Next page, please. But carbon recycling blast furnace cannot recycle all the CO2 from the process. So excessive CO2 must be recycled in the longer supply chain. Our idea is to make basic chemical material such as methanol by processing excessive CO2 from blast furnace by additional hydrogen. Then the methanol can be used to produce chemical products such as resin or plastics. After those chemical products are used in society and recycled back in the end of the life, blast furnace can use them as a reducing agent to further save the use of the coke, then save the CO2 emissions from the blast furnace. So ultimately, carbon recycling blast furnace combined with CCUS process in the longer value chain can be a zero carbon steel process, even continue using blast furnace. Next page, please. We know that each option has pros and cons, and there is no single bullet for zero carbon steel process yet. So JISF, Japan Iron Steel Federation, decided to pursue all the possible options in parallel. More realistic approach such as COS 50 and carbon recycle blast furnace may be developed and deployed commercially by the year 2030, then they can use existing blast furnace infrastructure to save capital cost. Then more challenging 100% hydrogen reduction will be commercialized at the scale during the 2040s to achieve carbon neutral by 2050. Next page, please. As you may have recognized, most of the zero carbon steel options requires massive hydrogen use as a non-carbon reducing agent. Also, steel products must be formed into final product shape, such as coils and pipes from ingot or slab shape. This downstream forming process also requires heating up steel to very high temperature. Zero carbon steel process need to use hydrogen rather than carbon fuel as heating fuel as well. Our calculation shows that as much as 7 million tons of green or blue hydrogen is necessary to produce current Japan's annual pig iron production, that is about 75 million tons. If the cost of such zero carbon steel should be equivalent to the cost of current blast furnace-based steel, we estimate that the cost of green or blue hydrogen in Japan must be as cheap as 8 yen per kilo H2. That is about 7 US dollar cents. If this is not the case, then if this is not the case in 2050, then the cost of zero carbon steel will be inevitably very expensive. Next page, please. So therefore, there are several challenges for the net zero carbon steel in real world. First, R&D costs should be massive. Though Japanese government decided to support R&D cost by about 200 billion yen for next 10 years, the amount is far less than the equivalent the subsidy to steel industry in the case of EU or China. Then even technologies are successfully developed, and then a massive scale investment to replace existing carbon-based steel process is necessary. Of course, ample supply of cheap hydrogen and affordable zero carbon electricities are preconditions for such investment of a new zero carbon steel process. Then in any case, zero carbon steel must be more expensive than current steel, though the spec and the functions of the steel itself remain the same, except for zero carbon feature. So steel customers and ultimately society itself need to bear the burden of high-cost zero carbon steel to make all the additional costs associated with R&D, commercialization, and full-scale operation of zero carbon steel compensated. The last page, please. The last year, Japan Iron Steel Federation issued a policy paper like this, in which we declared carbon neutral by 2050 and how we will achieve it. with various options. But at the same time, we have clearly identified the challenges in achieving it and ask the government and the society to share them, since we cannot solve them alone. And the zero carbon steel is a transformational social challenge in Japan. So the challenge is big, and the Japan and Australia can work together to solve all the associated the issues such as cheap and affordable hydrogen supply, continuous supply to the industry. Thank you very much for your attention.
Thank you very much for your comprehensive presentation, Mr. Tezuka. So the next we're gonna turn to Australia, and we will have two presentations. Let me introduce the two speakers together now. The next speaker is Professor John Pye. He is Associate Professor and Convener of the Renewably Refined Metals Program in the Australian National University's Grand Challenge, Zero Carbon Energy for the Asia Pacific. He obtained a PhD in solar thermal energy from the University of New South Wales. And our last speaker is Mr. Christopher McMahen. He is the Global Manager for Technical Marketing for Fortescue Metals Group. Fortescue Metals Group also operates Fortescue Future Industries, which is progressing major investments into production and the supply of green hydrogen and green ammonia for industry decarbonization. So Professor Pye and Mr. McMahen, the floor is yours, please.
Thank you, Professor Sugiyama. Can you see my screen?
Perfect.
Wonderful. Okay, well, thank you very much for the kind introduction, and thank you also to Professor Komiyama, Dr. Aisbett, and Mr. Tezuka for the interesting presentations that went before mine. It makes my explanations easier. So I'm going to talk about green steel and some Australian perspectives and some research priorities. Yeah, so I'm going to cover Australian ores and their impact and role in green steel making. It's an important aspect. I have some comments on how Japan and Australia can work together in this industry, and I want to describe some upcoming R&D activities and priorities. So firstly, on the Australian ores. It's very important to be clear that not all ores are equal. We have pellets, we have lump ore, we have iron ore fine concentrates, and just iron ore fines. And as you can see from these prices, which are for port side delivery prices of ore in China, this is wet metric tons in US dollars. As you can see, the percentage of iron in these different grades of ore is quite different, and some of them are fine particles like this here, and some of them are lumps as extracted, and then there are pellets which are already been partly reduced and partly treated, and the scale of difference in cost between these is nearly double. So there's a big variation in ore price, and partly this corresponds to the cost of the extraction and the processing, but it's a market situation, and it also very much depends on how much it costs to convert these different ores into steel. So some of the products require a lot more processing steps than others. So stepping over to the right, Australia has these huge reserves of cheap direct shipping ore, hematite. So hematite and direct shipping ores are typically in this category towards the bottom of the plot on the left. They're the lower cost ores and lower priced ores. But Australia has these enormous amounts of these ores and is the largest largest reserves and the largest producer. But its ores are not as high grade as some other countries. So Brazil, the Carajás area has large deposits of ore which can be extracted with 65% iron content. So there's a very big difference in the market position of different companies. And that's, all these prices reflect conventional processing. Future processing, things could change a lot. We've already seen a fair bit about the iron and steel process as it stands today. The blast furnace is the dominant route, and our ores are either directly shipped and sintered and put into the blast furnace, or sometimes we have lump ores, which can also be directly put into the blast furnace. and some ores are beneficiated and turned into pellets or sintered before they go in. This pathway is the pathway with high emissions, and it's the one we need to transform. In relation to how ore grades are affected through this process, we have these different ores with different iron percentages going into the global supply. One option is beneficiation. Beneficiation means separating out these gangue components, a large fraction of which are silica and alumina, separating them out. So we can beneficiate. This can be done by various processes that usually start with grinding the ore up into small particles. There are processes that are wet, there are processes that are dry, there are sifting and sorting processes, flotation, and most importantly, perhaps, there's magnetic separation. And this is a very effective way of increasing the grade of ore, but it works best with magnetite ores. These are not the same as the hematite ores that are predominantly exported from the Pilbara. So beneficiation, very dependent. How effective it is depends on the kind of ore you have, and it's not done to the majority of Australian ores currently. If you don't remove these gangue components at this step, then your choice is to add lime to the blast furnace, which bonds to those components and causes a liquid phase called slag to separate out and flow from the bottom of the blast furnace down in this area. So slag is the alternative way of removing these impurities. And that means that the later on stages of steel making don't have the same impurity load in them. If you follow a direct reduced iron making pathway, the treatment of slag is very different, and I'll talk about that in a moment. Yeah, so if we think about gangue in green steel processes, there's perhaps two categories of green steel processes that I'm going to describe. The top ones here are the direct reduced iron making pathways. So hydrogen direct reduced iron making is the kind of green steel pathway that's most advanced. And whether you're talking about a shaft furnace, which is like the kind of Midrex type process, or the Swedish Hybrit one that we heard about, then it could be a shaft furnace, which by the way uses pellets of iron ore all stuck together in a high temperature furnace, or a fluidized bed process, which can use the fine particles directly. Either one of these, they reduce the iron oxide to iron in a solid phase process. So any impurities that are present in the ore coming into this process remains locked in. There's no liquid phase, there's no opportunity to separate the slag. That means that all of the pressure on how to get rid of those impurities falls to the downstream processes, which we might loosely refer to as steel making. But whether it's an electric arc furnace, melter, a basic oxygen furnace, or some combination of these, there's going to be lime that we then need to use in this stage to remove those impurities. That's going to require additional heating to finally melt those components. And the differences in the process raise questions about whether the slag material, and I didn't mention earlier, slag is a valuable material. It can be used to replace cement, and so it has a value in the market. But when you follow this alternative pathway, there are questions about whether it still has that same value. And increased alkalinity and viscosity and handling issues can result in some of this slag simply being put in landfill instead of being a useful product. So if we have large amounts of gangue and we're trying to make green steel, it imposes some increased costs in this downstream step. If there are increased costs here to remove the gangue, then of course we can remove it up here instead. So increasing the amount of beneficiation is another option. But the beneficiation, again, is very dependent on which kind of ore you have. If you have magnetite, then you have this magnetic separation option. If it's hematite, then the grinding costs are different. The magnetic separation processes work a bit differently. So we have a lot of things to understand and work out for how different ore grades affect how green steel production will work. And to finish on this slide, molten oxide electrolysis and processes like Hisana combined with carbon capture and storage are interesting because slag separation is possible. Right, I'm going to move on and talk a little bit about the Japan and Australia aspects here. I want to mention the renewable energy resources. So the Pilbara area, where all this ore is from, is an amazing area for solar energy. And compared to, for example, Kurashiki, where a large amount of steel making is done in Japan, solar energy is going to be about 40% cheaper over here. Solar energy is going to be about 40% more expensive in Japan. If we look at wind power, then Japan has this large offshore wind resource. It's very actively developing that at the moment. But I thought it's worth mentioning the mean power density in the Pilbara area is about half what this offshore resource has. But then offshore wind may cost double the price of onshore wind. So I think there's some questions to be addressed here. So the renewable energy resource, in combination with proximity to things like potential hydrogen storage, ore deposits, and of course established steelmaking, makes a complex picture that we need to really figure out. I don't think I need to talk too much about the future iron making, but there was a question about hydrogen injection into blast furnaces. That's something that's been tested already in the last couple of years in Germany. And I wanted to also highlight this very exciting hydrogen-based iron making process, which is happening with Japanese support. Mitsubishi Heavy Industries operates Prime Metals as a subsidiary, and they're developing a fluidized bed iron making system, which I think is very applicable to Australian ores potentially. Different analyses of what's going to happen in green steel come out with different answers. On the left, this one is all about near-term costings and not really about total decarbonisation, incomplete decarbonisation. And the findings when you take that approach is that CCS and incremental changes to blast furnaces are the cheapest and have the lowest cost of abatement. But if you take it as given that you need to completely decarbonise your steel industry because of environmental imperatives, then you need to think also about, so you have a different set of potential processes then, but also you need to think about how the costs of renewable energy and hydrogen are going to change over the coming years. In the last 10 years, solar and wind have dropped by 70 to 90% in cost, and that's forecast to continue. Electrolyzers as well. This analysis from Bloomberg suggests that both hydrogen direct reduced iron making and molten oxide electrolysis can reach by 2050 the same price range as current iron and steel. So to the Japan-Australia thing, I think a really important problem that we have to figure out is how to put together a steel industry that's overall the cheapest and most efficient. And there are a number of important configurations to think about. We can keep doing what we do, ship or do all the processing offshore. So in the case of Japan, you would need to do sintering and pelletization, hydrogen iron making, downstream processes. You would need to supply the energy for this from, for example, offshore wind, shipped in ammonia and hydrogen, and you could do that. You could move the first step, the pelletization, upstream. You could also move the whole HDRI process upstream and do all of that energy intensive stuff in Australia and ship the pig iron to Japan and do all of the high-end engineering and downstream manufacturing still exactly where it is. You could shift it all to Australia, but I don't think that's a very good idea. The Pilbara is a very hot, remote area, and it doesn't have a lot of complementary industry. So I think somewhere in the middle here are the really interesting arrangements that we should be analysing and figuring out. I'll talk about the upcoming R&D. We have announced and are commencing work in a new heavy industry low carbon transition cooperative research centre, HILT CRC. This program has funding from the Australian government as well as a number of core and key partners who are all investing as well. We're going to be looking at process technologies for iron, alumina and cement, some cross-cutting technologies including hydrogen, heat and carbon capture and utilisation, and policy, economics and social issues. And the program has, as part of it, a sort of a regional hub focus. So there's going to be looking at integrated approaches for the Pilbara, which is the iron ore mining area, the Upper Spencer Gulf, where our project partner Liberty has its iron and steel operations and magnetite resources, and also northern Tasmania, where Grange Resources produces pellets for export. I wanted to highlight our Japanese involvement. We have Mitsubishi Heavy Industries and their subsidiary Prime Metals, and also another MHI business, the hydrogen utility, already in this program. And I'll highlight this project, which I'll be leading and starting very shortly. This is going to be our attempt to get across all of those gangue removal and purity issues. We're going to be looking at a number of pathways from extraction of ore to final steel making, and looking at what the optimal configuration of this process is, whether we remove the gangue upstream or downstream, and which pathway gives the best option. And we're interested again in this fluidized bed process, which allows you to avoid the sintering step, which is responsible for 15% of emissions or so. I have a long list of really interesting research topics here, which I don't want to go through. The bold ones basically were being addressed in the CRC. But there are other ones. Maybe I'll just touch on this CO2 splitting thing. There was some mention by Mr. Tezuka about carbon capture and utilization, and there's some work at the University of Melbourne, a Carbolec project to look at methods of CO2 splitting, which turns CO2 into a valuable fuel or a feedstock. There's also an interesting project in the Phoenix CRC, another cooperative research centre, on ammonia-based iron making. So lots of important and interesting topics that I think we need a range of different approaches to solve the challenges of green steel making, because no single pathway has all of the problems solved yet. So I'll conclude my presentation. The first point I want to emphasize is that Pilbara ores have higher gangue content than the Brazilian hematite ores, and so they're harder to beneficiate also than magnetite ores. So it's a little bit of a not trivial issue to develop these optimized processes for green steel processing that can accommodate the gangue. And because iron ore is a major export for us, it's a key strategic challenge for Australia. There's also this question about carbon capture and storage versus hydrogen, and I think there is wide variation in the conclusions and the analysis here, but it's critical to consider how technologies are going to reduce in cost, and you cannot overlook the 90% reductions in PV prices over the last 10 years when you think about what to invest in going forward. And finally, I think there's some really interesting work to do between Japan and Australia to examine the best way to couple Japan's major steelmaking experience and industry with Australia's iron ore and renewable energy resource. And I think there are future configurations that could be figured out that would lower the overall costs of green steel as we go forward. That's the end of my presentation, and thanks for all of the contributions of my colleagues and the funding support, and a return to the moderator, Professor Sugiyama. Thank you.
Thank you, John. And our next speaker is Mr. Chris McMahen. Please, Montesquieu Group.
Thank you, Sugiyama-san, and thank you, John. Good afternoon, all the participants, and thank you for the opportunity to contribute to the conversation. Let me say at the outset that I won't be sharing any slides. The previous 4 speakers have already shared a wonderful set of slides that really do quite adequately describe the situation and the topic of discussion. And I've been invited to contribute by providing the perspective from a major iron ore supplier. And Mr. Sugiyama did introduce me as representing Fortescue Metals Group. We are the 4th largest supplier of iron ore to the seaborne market. And in the last completed financial year, we produced and supplied 185 million tonnes of hematite goethite ore from our operations in the Pilbara. The average iron content of that ore was 57.5%. Emma, in her slide, mentioned the scale of the iron ore business in the Pilbara. Along with our competitors, we supply around 900 million tonnes per annum of hematite goethite product to the seaborne market. And the vast majority of that product is consumed in the blast furnace BOF route of iron and steel making. There is a small and growing magnetite business in the Pilbara. Fortescue itself is progressing a project at Iron Bridge, which will be completed towards the end of this year, and that will add a further 22 million tonnes of magnetite product to our portfolio. But my comments today will be directed at the hematite goethite business of ourselves and the competitors in the Pilbara. So I'll be talking at a relatively high level to the topics that the previous presenters have already introduced. But if I could simplify the situation for the hematite goethite Pilbara suppliers as one of very large scale, low cost production of direct shipping ores, or DSO. Now there's little beneficiation type processing in the vast majority of this DSO. It's primarily dry crush and screened into sinter fines and lump. There is some beneficiation processes employed. In fact, Fortescue has beneficiation processes at several of our mines, but it's not across the whole suite of the products. And the technology employed is focused largely on a relatively simple separation using water washing or suspension, and then separating differential minerals by their density or size characteristics. Now, there are a few examples of more complex beneficiation in the Pilbara. There's some dense media, or DMS, employed at some mine sites, and we in fact ourselves employ wet high intensity magnetic separation on one of our sites, but it's a very small part of the side stream of the main processing. The adoption of these more complex beneficiation processes, and John referred to them as being predominant in places like South America and North America. The thing that holds them back in the Pilbara is not only the cost of the processing, but also the product upgrades that are achieved, and also the total product recoveries are relatively low. And this is due to the nature of the minerals. So if I could sort of further simplify all of that and summarize the processes in the Pilbara as the identification, differentiation, and separation at a mineral level. So separating iron oxides from other non-ferrous oxides to the best of the processing's ability, and delivering those direct shipping ores to the integrated steel industry. The conversation today has really been around challenging that existing Pilbara iron ore industry to move processing from the iron and steelmaking industry further along the supply chain towards us. And again, I could simply summarize the iron and steelmaking processes as performing a similar separation, but rather than at the mineral level, it's at the molecular level. So reducing the iron oxide to molten iron and separating the various gangue minerals and other metals into slags. So that's a paradigm shift for the operations in the Pilbara. There's a number of things, number of challenges and opportunities which we have to address when considering decarbonisation of our own industry and of the iron and steel industry. Reduction technology is certainly a key consideration and a focus, but so too are the raw material inputs to that reduction process and the resultant products out of any alternative iron and steel making process, particularly if they are to be undertaken in the Pilbara. So that's the general situation in the Pilbara. More specifically to our circumstance at Fortescue, we've set ourselves three very ambitious goals with regards to emission reduction targets. The first one is for our iron ore operations. We're targeting carbon neutrality for scope 1 and 2 emissions across the entire operations by 2030. The second target is a 7.5% reduction in scope 3 emissions related to our iron ore products in their process of iron and steel making by 2030. And the third very ambitious target is for net zero scope 3 emissions related to the iron ore business by 2040. So that puts our targets well ahead of many of our existing customers in the iron and steel making industry. So some very big challenges for us. So to achieve these ambitious targets, Fortescue is leveraging its investment in renewable energy projects via our wholly owned subsidiary Fortescue Future Industries, or FFI. So FFI is advancing a suite of global products to deliver in initial stages 15 million tonnes per annum of green hydrogen and or green ammonia by 2030. Particularly this green hydrogen can be utilised by Fortescue's iron ore business in our operations for decarbonisation, but also for the production of green iron and steel. Alternatively, or in addition to this, we can also supply green hydrogen and or green ammonia and or green iron and steel products to our existing customers and transitioning iron and steel business. So just turning to our R&D programs and our focus on this challenge, the way we are approaching it. Firstly, with regards to the reduction technologies that have been spoken about, we're investigating those. So we're developing internally our own new and novel green iron and steel making technologies. We have placed a particular focus on electrolysis technologies, which can maximize the use of renewable electricity without the need to convert to hydrogen. But we are also evaluating existing and emerging alternative iron making technologies that are utilizing direct reduction and hydrogen, both in shaft furnace and fluidized bed. So that's the reduction type technologies themselves. In regards to the preparation of feedstock or materials, we're evaluating the performance of various Pilbara iron ore minerals in those technologies. And we're also exploring the use of renewable energy in traditional and emerging beneficiation technologies to improve the performance of the products in both the current technologies, BF, BOF route, and as preparation for future or alternative reduction technologies. We're also leveraging the availability of renewable energy for further processing of some of those potential reduced iron products. So further from DRI into HBI, potentially pig iron, crude steel, and even semi-finished steel products. And the third stream of our R&D work is techno-economic evaluation. So very tight cost benefit analysis of each of the steps in that value chain I just described. We need to determine the optimum point of return on investment, not only of capital funds, but also of effort. And we're doing this in various operating scenarios. So clearly in the Pilbara, in our current operating situation, but also we're extending this to our customers' situation and circumstance, and also emerging production facilities. So just in summary, as there'll be a number of alternative iron and steel making technology choices for a transitioning industry, and the pace of adoption, it will be varied across and within the markets, and different technologies will suit different participants. Fortescue is pursuing a strategy which may actually lead to us supplying a multitude of products for various solutions. It begins with the ongoing supply of existing low-cost DSO, but it extends through to reduction technologies, DRI, HBI, potentially even non-traditional HBI, so lower FE content or higher gang content HBI, which may be of use to existing blast furnaces. But it extends all the way through to pig iron and semi-finished steel. We're collaborating with our existing customer base on these options, but we're also extending the engagement to new market entrants. We're working with engineering companies or solution providers in the technology space, and with research institutes such as John's and some of the projects he's already outlined in his presentation. That was it, Mr. Sugiyama. If there are any questions, I'd happily take them on board.
Thank you, Chris. And unfortunately, we ran out of the time. So, but I saw the Q&A box, and there were a lot of lively exchange on very important topics. So it was great to see that. So there was an important question about the sharing of the slides. We didn't get the explicit permission from the presenters, so we will talk to the speakers, and we're gonna put something on the web if that is possible. Anyway, in any event, our intention is to put a recording on the web, so you might want to come back to our website in the near future. I would like to thank everybody, all the speakers and all the participants for joining us today on this very important topic of low carbon steel and decarbonization, both in Australia and Japan. I would like to close this meeting, and please, the four speakers, please stay in the same link, but for the audience, please leave the Zoom room. So thank you very much for all your active participation. Thank you.